People often say that light is both a wave and a particle, as if it exists somewhere in between the two. But when I explain this, I say something very different. Light is neither a wave nor a particle. It is something completely different. And if you don't understand this difference, you're not really learning quantum mechanics. You're memorizing a misleading analogy. Let me explain what light actually is. Because the wave-particle duality story that everyone repeats is wrong. Not slightly wrong, but fundamentally wrong. And it's taught in almost every physics class as if it were unquestionable truth. You've heard it before. Light is both a wave and a particle. Everyone has. It sounds deep, mysterious, very quantum, very profound. But it's nonsense. Light is not a wave. Light is not a particle. Light is not both. Light is not either. Light is something else entirely, something we don't have a good everyday word for. So we rely on analogies. We say wave and particle because those are familiar concepts. But these analogies break down. They mislead. They make you feel like you understand, when in reality you don't. I'm going to tell you what light really is. Not the textbook simplification, not the popularized version, but the actual physics. It will sound strange because light is strange. Nature is strange. And trying to force nature into familiar classical categories is exactly what creates all this confusion. To understand how this confusion started, we need to look at history. In the 1700s, Newton argued that light was made of particles, tiny bullets shooting through space. This explained why light travels in straight lines, why it casts sharp shadows, and why you can't see around corners. It made sense, but then a problem appeared. Thomas Young performed his famous double-slit experiment. He shone light through two narrow slits, and instead of seeing two bright regions on a screen, as particle theory would predict, he observed an interference pattern, a series of alternating bright and dark bands. That's a wave phenomenon. When waves overlap, they interfere. Peaks add to peaks, troughs cancel peaks, and that produces exactly the pattern Young saw. So light must be a wave, right? In the 1800s, Maxwell developed the equations of electromagnetism, and what emerged naturally from the mathematics were waves, electromagnetic waves. Light was identified as an electromagnetic wave, oscillating electric and magnetic fields propagating through space. It was elegant and beautiful. It seemed like the problem was solved, but it wasn't. In the early 1900s, Planck studied blackbody radiation, the way hot objects glow. As objects get hotter, they glow more intensely and change color, red hot, white hot. Classical wave theory predicted the spectrum completely wrong. It predicted infinite energy at short wavelengths, a result known as the ultraviolet catastrophe. Obviously, that couldn't be right. Planck fixed the problem by assuming that energy is emitted in discrete chunks, or quanta. Light wasn't emitted continuously. It came in packets, each with energy proportional to its frequency, E equal to hf. The math worked perfectly. But Planck himself didn't believe this was a real physical property of light. He thought quantization was just a mathematical trick, a feature of how atoms emit light, not of light itself. Then Einstein came along with the photoelectric effect. Shine light on a metal, and electrons are ejected. But the details were strange. The energy of the ejected electrons didn't depend on the intensity of the light. It depended on the frequency. Blue light produced higher energy electrons than red light, no matter how dim the blue or how intense the red. This made no sense if light were a wave. In wave theory, higher intensity should mean more energy delivered. But that's not what happened. Einstein proposed that light itself is quantized. It consists of particles called photons. Each photon carries energy hf. When a photon hits an electron, it transfers all its energy at once. One photon interacts with one electron. Intensity only determines how many photons arrive per second. Each interaction is particle-like. So now light seems to be particles again. Newton appears vindicated. Except for one problem, the double-slit experiment still works. You can do it today and still see interference. That's a wave phenomenon. Particles don't interfere with themselves. So what is light? A wave? A particle? Both? Neither? This is where the confusion really begins, and it has confused people for over a century. Textbooks say that light exhibits wave-particle duality. Sometimes it behaves like a wave. Sometimes it behaves like a particle. Which behavior you see depends on how you measure it. This idea is often tied to Bohr's principle of complementarity. Wave and particle pictures are complementary descriptions. You can't see both at the same time. Each is incomplete on its own. But I don't like this explanation. It's too vague and too philosophical. What does sometimes wave, sometimes particle actually mean? When does light decide? How does it know what kind of measurement you're performing? There is a better and more precise way to think about it. Light is neither a wave nor a particle. Light is a quantum object. It obeys the laws of quantum mechanics. And quantum mechanics does not say that things are waves or particles. It says that systems are described by probability amplitudes, complex numbers that evolve according to specific mathematical rules. Calculate these amplitudes t, and you square them to get probabilities. That's quantum mechanics. Sometimes when you calculate these amplitudes, the mathematics looks like wave equations. You see interference, diffraction, and superposition. So we say the system behaves like a wave, but it is not a wave. It is a quantum object whose probability amplitudes interfere. Other times when you detect light, you observe localized discrete events, individual clicks in a detector. One photon, one click. So we say it behaves like a particle, but it is not a particle. It is a quantum object whose probability amplitude has collapsed into a localized detection event. The wave behavior describes how probabilities are distributed in space. The particle behavior describes how detection occurs in discrete localized events. The underlying reality is neither classical waves nor classical particles. It is quantum amplitudes. Consider the double slit experiment again. You shine light at two slits. Classical wave theory says the wave passes through both slits, splits, and interferes with itself on the screen. Classical particle theory says each photon goes through one slit or the other, producing two bright regions. Neither description is correct. Quantum mechanics says that each photon has a probability amplitude for going through slit A and a probability amplitude for going through slit B. These amplitudes add together. They interfere. The interference of amplitudes determines the probability of where the photon will L be detected. The photon does not literally split like a wave, and it does not choose a single slit like a classical particle. It does something that cannot be described in classical terms. The amplitudes interfere. That is the correct description. When the photon is detected, it appears at a single point on the screen. That looks particle-like. But the pattern formed by many such detections is governed by interfering amplitudes, which looks wave-like. It is neither. It is quantum. What really bothers me about wave-particle duality language is that it makes people think light switches between being a wave and being a particle, as if it changes its nature depending on circumstances. That is not what happens. Light is always the same thing, a quantum object. What changes is how we interact with it, how we measure it, and how we describe the measurement. If you don't measure which slit the photon goes through, the amplitudes for both paths interfere, and you see an interference pattern. People say it behaved like a wave. If you do measure which slit it went through, the interference disappears. You see two bright regions, and people say it behaved like a particle, but the light didn't change. Your measurement changed. Your interaction with the light changed. The light simply followed the rules of quantum mechanics. Now consider electrons. Electrons are usually thought of as particles. They have mass, charge, and seem localized. But perform a double-slit experiment with electrons, sending them one at a time, and you still get an interference pattern. Does that make electrons waves? People say electrons also exhibit wave-particle duality. In fact, they say all matter does. De Broglie wavelengths. Everything is both wave and particle. But this is the same mistake. Electrons are not waves. They are not classical particles either. They are quantum objects. Their probability amplitudes interfere, and that's why you see interference patterns. You can do these experiments with atoms, molecules, even larger systems. As long as you preserve quantum coherence and avoid decoherence, interference appears. Not because these objects are waves, but because they are quantum systems whose amplitudes interfere. The wave language comes from classical physics. In classical physics, there are only two categories, particles and waves. Particles are localized, have definite positions, and follow trajectories. Waves are spread out, have wavelengths and frequencies, and interfere. When quantum mechanics revealed phenomena that fit neither category, people tried to force them into those old boxes. Sometimes wave, sometimes particle. Dual nature. But that's wrong. Quantum objects are a third category entirely. They obey quantum mechanics, which does not reduce to classical wave theory or classical particle theory. The mathematics of quantum mechanics uses complex probability amplitudes. These amplitudes evolve according to equations like the Schrödinger equation, or in quantum field theory, according to field equations. To get probabilities, you square the amplitudes. When there are multiple possible paths or alternatives, you add the amplitudes first and then square. That addition is what produces interference. That's the whole story. No classical waves, no classical particles. Just amplitudes following precise mathematical rules. Why do we keep using wave and particle language? Because it's a useful approximation. In some situations, quantum systems behave approximately like classical particles. In others, the math resembles classical wave equations. As a teaching tool, this language helps beginners connect new ideas to familiar ones. But it's a crutch. And if you never let go of it, you'll never truly understand quantum mechanics. You'll stay stuck thinking things are mysteriously both and neither, dependent on observation, consciousness, or philosophy. That's not physics, that's confusion. This is how I teach it. I don't start with waves or particles. I start with probability amplitudes, complex numbers with magnitude and phase. They evolve in time. You add them when multiple possibilities exist. You square them to get probabilities. Then I show examples. The double slit experiment arises not because light is a wave, but because amplitudes from different paths add and interfere. Localized detection events occur not because light is a particle, but because measurement yields discrete outcomes. Build the theory this way, amplitudes E. Evolution, measurement, no waves, no particles, just quantum mechanics. When students understand this, they stop asking whether something is a wave or a particle. They stop trying to visualize what an electron really looks like. They stop thinking observation creates reality. They understand that quantum mechanics is about calculating probabilities. You have amplitudes, you evolve them, you predict outcomes. Everything else is interpretation, philosophy, not necessary for doing physics. You might then ask, what is an amplitude? What is this complex number physically? I don't know. Nobody knows, and that's fine. The amplitude is a mathematical object that lets us calculate probabilities. We know how to use it. We know the rules. We compare predictions with experiments, and they agree perfectly. What it is at a deeper level, I can't tell you. Maybe it's physical. Maybe it's epistemic. Maybe those categories don't even apply. Physicists have debated this for a century. Copenhagen, many worlds, pilot wave, cubism. Each has supporters. Each has problems. Experiments don't distinguish between them. So I don't worry about it. I calculate, I predict, I compare with experiment. It works, that's enough. But I'm careful about language. I don't say light is both a wave and a particle because that's misleading. It suggests that light switches between two classical forms. Instead, I say light is a quantum object. It behaves according to quantum mechanics. Sometimes its behavior resembles waves. Sometimes it resembles particles, but it is neither. It is quantum. This is more precise, more accurate, and less confusing. And the confusion really matters, because once you start thinking light is both a wave and a particle, you start asking the wrong questions. You start thinking observation determines reality. You start bringing in consciousness, mysticism, and ideas that have nothing to do with physics. I've seen this happen. People take wave-particle duality and conclude that quantum mechanics proves reality is subjective, or that consciousness creates reality, or that you can manifest things just by observing them. That's nonsense. That's not what quantum mechanics says. Quantum mechanics says you calculate probability, amplitudes, and predict probabilities. That's it. Taking wave-particle language, too, literally leads people astray. That's why I'm careful. I use precise language. I emphasize the mathematics, not because I want to make things boring or inaccessible, but because I want people to understand real physics, not a distorted, popularized version of it. Light is not a wave. Light is not a particle. Light is a quantum object described by probability amplitudes. Sometimes the rules governing those amplitudes produce patterns that look wave-like. Sometimes they produce localized detection events that look particle-like. But the underlying reality is quantum, not classical, not a hybrid of classical ideas, just quantum. And if you understand that, really understand it, then you're on your way to understanding quantum mechanics. Not perfectly. Nobody does. But accurately, without the confusion that comes from forcing quantum phenomena into classical categories. That's what I try to teach. That's what I wish everyone understood. Quantum mechanics is strange, yes, but it's not mystical, it's not paradoxical, it's just different from classical physics. Learn the rules, calculate with amplitudes, predict outcomes, compare them with experiment. That's physics. Not by calling light a wave or a particle or both, but by treating it as what it actually is. A quantum object that follows quantum rules.